All right, great. Well, welcome everyone to our MPRINT Hub webinar for December, the educational aspect of the webinar. We're pleased to see Dr. André Dallmann here today to talk about physiologically based genetic modeling. So, André, I will pass it over to you to introduce further.
Thank you, Sarah. Happy to be here. So I'm André Dallmann. I'm working as a scientist for systems pharmacology at Bayer. And today I have the pleasure to present about the postpartum PBPK modeling for amoxicillin. Let me just set up the screen here. Okay. Can you give me feedback if you can see the presenter mode?
Yeah, it looks good. Thank you.
Great. I can't see any raised hands, so if there should be questions during the webinar, I mean, either interrupt me or we can discuss them later after the presentation. Okay, so first of all, a short disclaimer. I have no financial relationships to disclose relating to this presentation. I am an employee of Bayer AG, and I use the open systems pharmacology software tools and models in my professional role. And the views expressed in this talk represent my own opinions. So drug use in the postpartum period is quite frequent and remarkably high. So this figure is taken from a study that was conducted a couple of years ago in Norway, in Northern Europe. And what we see here is that the women that use at least one prescription drug before conception, during pregnancy, and then 3 months after delivery is basically highest after birth, 3 months after delivery, which is quite surprising. These study findings are not an exception. I mean, similar findings have been reported by other authors, and this is just another study from the Netherlands that compared then drug use in the postpartum period between women who breastfed and women who did not breastfeed. And the authors found that breastfeeding women seem to be more reluctant to use drugs. Also highlighted in this table here is the percentage of anti-infective drugs that are used during the postpartum period. And we can see that in both groups, the anti-infective drugs, to which also amoxicillin belongs to, which I will talk about later, are among the highest or most used drugs in this population. Now, when we think about pregnancy, so the period preceding the postpartum period, we know that virtually all organ systems undergo changes that result in many cases in significantly altered pharmacokinetics. So, for example, we know, as shown on the left here, that the activity of many enzymes is increased during pregnancy. Not all, some decrease in activity. We also see an increase in the glomerular filtration, in the net tubular secretion. Also, the total body composition is very different in pregnancy. I mean, total body water and fat mass both increase. Plasma volume increases as well, and as a consequence, many plasma proteins like AHE and albumin are diluted, so their concentrations decrease during pregnancy. And all of this obviously has an effect on pharmacokinetics during pregnancy. Now, what is quite remarkable is that these changes during pregnancy are built up over a period of 9 months. They often peak at the end of pregnancy. And after delivery, after childbirth, almost all organ systems change back to the baseline level, so meaning to the value before conception. and that within an even shorter time interval. So really the dynamics are quite high in the postpartum period. And I think it's also quite evident that these changes they do not always, but they may also substantially affect drug pharmacokinetics, especially in the early postpartum phase. So data on the physiological and anatomical changes in the postpartum phase are quite scarce. And a couple of years ago, we conducted a study, a literature search, to collect all studies reported in the scientific literature that reported on changes in relevant physiological or anatomical parameters during the postpartum period that could subsequently be implemented in a PBPK modeling framework. Now, after screening the literature, we came up with a total of 105 studies that reported almost 1,100 data values for a given physiological parameter. And these data values were retrieved from more than 3,700 women in the postpartum period. These data were collected ranging from 1 hour after delivery to as much as 130 weeks after delivery. On the histogram on the right side here, you can see I say the distribution of the absolute frequency of parameter data throughout the postpartum phase. And I mean, luckily, 46% of all data were reported for the first 8 weeks after delivery, and almost 70% of all data were reported within the first 16 weeks after delivery. So looking closer at what we did now with these data, we conducted a nonlinear regression analysis. So meaning that for each physiological parameter, that data were, say, analyzed in an automated manner, conducting nonlinear regression analysis using the software R. So we fitted different types of functions to the observed data for each physiological parameter. A linear function, polynomial functions of second, third, and fourth degree, different types of sigmoidal functions, and abatement function in case of non-monotonic trends. So, for example, during pregnancy, I mean, almost all parameters, they either increase or they decrease, but they always go in one direction, either up or down. And during postpartum period, we've seen that some parameters basically change their direction. So they might go down and then they increase again towards later stages of the postpartum period. After fitting all these different types of functions to our data sets, we selected the best performing function based on numerical and visual diagnostics. So as numerical diagnostics, we used the corrected ICAR key information criterion. And as visual diagnostics, we just plotted the data together with the fitted function and assessed whether whether any given function potentially overfitted the data. So we asked questions, I mean, does the function correspond too closely to the observed data? Can the function potentially fit additional data reliably that might pop up at a later stage? And finally, is the function biologically plausible? And I'll have an example to show that in a minute. So in the end, that gave us functions for each physiological parameter and thus a continuous description of the changes in the mean value of a given parameter that we wanted to plug into a postpartum PBPK model. Here on this slide, I show the cardiac output as an example. So on like y-axis is the cardiac output in liters per minute. The x-axis is then our independent variable, the time after birth here in weeks. And the gray circles are reported data in the literature for the cardiac output at any given stage after delivery. The size of the circles represents then the number of study subjects where the cardiac output was measured. So the smallest circles would be individual measurements, and the larger circles would be mean data from more than one woman, basically. And the different lines in the different colors indicate then the different functions that we have fitted to the data. And the dashed red line here is the level that we have observed prior to pregnancy. So that was, say, the baseline that we expected would have been reached sooner or later. As you can see, the different types of functions describe the data more or less well. I mean, not surprisingly, the linear function, the light gray curve, doesn't describe the data very well. However, the dark blue curve, the fourth order polynomial function, appeared to describe the data best if we just look at the corrected IKK information criterion. So that's given here in the parentheses. And a value of 0 would mean that this is mathematically the best performing function. However, looking at the, say, at the shape, at the trend of this function, you see that, well, maybe this function is really, say, closest to the data, but it's biologically implausible. So it really oscillates around there. This doesn't make sense. So in this case, then we selected the next function, so mathematically the second best function, which was then the 3-parameter logistic function that is also shown here on this slide. Now this we repeated these types of iterations for all parameters where we found data, and on the next couple of slides I'll just go through them, through a couple of them, not all. Here on this slide, we can see different parameters relating to the kidney. On the in the left panel, we see the kidney volume. Now the kidney increases in size during pregnancy, mainly because of hypertrophy, but there's also some discussion on whether or not there's hyperplasia, so real cell growth. That's not so clear from the literature. And after delivery, the kidney then shrinks back to its original size that it had prior to conception, within a time interval of approximately 7 to 8 weeks. In the middle panel, we see the effective renal plasma flow. And I mean, that's quite an interesting parameter, because just looking at the data, it seems that it decreases after delivery, drops below the pre-pregnant level, and then increases again. However, as you can also see, data were quite scarce for the effective renal plasma flow here, especially for the period, say, for the first 5 to 8 weeks after delivery. So, I mean, here it could be that our function does not describe the true trend, but just because data were missing, we have this kind of drop in there. And then finally, in the right panel, you can see the glomerular filtration rate. Now, at the end of pregnancy, it's about 34% higher compared to the pre-pregnant level, and then it drops also quite fast back to the pre-pregnant level, which is shown, indicated here in all plots by the dotted blue line. Now here again, we didn't have, unfortunately, so much data that were informative for the period between 2 to, let's say, 8 weeks after delivery. So I mean, here we also assumed that essentially by 2 weeks after delivery, glomerular filtration rate had returned to its pre-pregnant level. In addition to that, the serum protein concentrations are also quite relevant parameters because they can have an impact on the unbound fraction of a drug in plasma. And we see that basically both albumin and the alpha-1 acid glycoprotein, AAG, plasma concentrations decrease during pregnancy. That's a dilution effect because the plasma volume increases during pregnancy. And then after delivery, plasma volume shrinks again, and the albumin and AAG plasma concentrations rise again. Now here again for AAG, we saw a quite interesting pattern. So it's not only the concentration does not only rise until it reaches the pre-pregnant level, but it really like rises above the pre-pregnant level, peaks around 1.5 weeks after delivery, where it's about 84% higher versus the pre-pregnant level, and then gradually decreases until by 7 weeks it reaches the level that was measured before pregnancy. So to put these all together in a summary chart, gives us then the plots shown on this slide here. On the left, we see the weight of the different organs that were accounted for in the PBPK model. And on the right, we see then the blood flow for each of these organs. So these changes were all integrated in say, a PBPK modeling framework in a database that we used to construct the physiological basis of a postpartum PBPK model. Now, before diving into then the, say, the real modeling application work, I want to quickly look at the fraction unbound in the postpartum period, because that's also quite a relevant parameter when predicting the pharmacokinetics. And using the functions that we've developed to describe the trends seen in albumin and AAG concentrations after delivery, we can use a method proposed by McNamara and Alcorn to basically estimate the fraction unbound during the postpartum period for drugs that are mainly bound to albumin or AAG, based on the fraction unbound in adults, so the pre-pregnant fraction unbound, and the plasma concentrations of albumin or AAG in pre-pregnant individuals and in individuals in the postpartum phase. Now here, this function is the variable. So this function was developed to estimate the fraction unbound in infants. But I mean, you can just replace then this subscript infant basically with postpartum, and then you can apply this function to the postpartum phase. So we used this equation to predict the fraction unbound at different stages during the postpartum phase, and we evaluated it through comparison of the predicted values with observed values that we had taken from the literature. Unfortunately, there were not many data available for drugs that bind predominantly to AAG, so therefore we could not really evaluate this method here for drugs that are bound to AAG. In the right plot then here, you see the predicted fraction unbound versus plotted against the observed fraction unbound for drugs that are predominantly bound to albumin. The solid blue line is the line of identity. The dark blue area is the 1.5-fold error range, and the light blue, the light blue outer area is then the 2-fold error range. And I mean, luckily, about 77% of all fraction unbound values were predicted within a 1.25-fold error range. So that gave us quite some confidence that we can use this method in the also to predict the fraction unbound basically in postpartum women. So this brings us then to the next section, to like really the development of the PBPK model. And I'm not sure how familiar each of you is with PBPK modeling, so I've therefore also included a few slides just introducing PBPK modeling. So PBPK modeling is like a mathematical modeling technique that is used to predict all processes of pharmacokinetics, namely the drug release from its formulation, the absorption, distribution, metabolism, and excretion of a drug or any other chemical substance in humans or other animal species. PBPK models are compartmental models, and each compartment of the model represents a single organ. So therefore, we have a kind of, say, a physiological basis of PBPK models. All these compartments are then connected via the blood flows in a physiologically plausible manner. Each organ compartment can then be further subdivided into vascular, interstitial, and intracellular compartments. And yeah, as I said, the compartments are arranged in a parallel circuit to reflect basically the circulatory system. And thereby the drug movement in the body is mapped to a physiologically realistic structure. And what is important, like an implicit assumption here that is quite important, is that there's a clear and explicit distinction between the properties of the organism, the system-specific parameters, anatomical physiological parameters, and the properties of the drug, the things like molecular weight, lipophilicity, and so on. This slide here shows then the organ structure of any compartment in a PBPK model, as it is subdivided into the vascular space, the interstitial space, and the intracellular space. The small blue circles represent drug molecules, and they flow into each compartment via the blood flow. From there, they can cross the endothelial membrane to go into the interstitial space, and from there they can then cross the cellular membrane to reach the intracellular space, where metabolism may occur or not, depending on the type of drug and the type of organ. Now, to describe then the say the change of drug concentrations over time, the most basic type of ordinary differential equation is given here, and that's also really the only ordinary differential equation in my presentation. It's quite basic, so elimination is not accounted for in this equation, and also some other processes are not accounted for. But what you can see from this equation, why I put it on the slide here, is that all parameters in this equation can be informed from the data that we've collected in the literature. So we have Q, our blood flow, we have our organ volume here, we have K organ, that's the partition coefficient that type of quantifies like the extent to which a drug diffuses into the organ and to which extent it remains in the plasma. And this partition coefficient is then also calculated from properties of the drug and also from the tissue composition of any given organ. Okay, there are different types of PBPK modeling softwares out there, and the software that I've used is the Open Systems Pharmacology. This includes PKSim and Mobi, and toolboxes for R and MATLAB. All of this has been published as open source freeware, released under GNU Public License version 2. OSP GitHub, a screenshot is shown here on the right side, and the link is given here, is the main place for interactions. So on OSP GitHub, you can access the source code of PKSim or Mobi. You can find manuals, tutorials on how to use the OSP software suite. There are also repositories for PBPK models and systems pharmacology models. So, for example, the amoxicillin model that I'll present in a minute can be also found there and downloaded. And there's also the extension of PKSim to postpartum populations is possible via a dedicated postpartum database. That is not part of the official release, but you can still use it, and this can also be found on OSP GitHub. So then looking a bit at the concept of PBPK model translation to special populations, it's always the same concept. So first you build a PBPK model for a reference population for adults. So you have again the drug properties here, things like lipophilicity, molecular weight. Then you have the organism properties, and those are the system-specific properties, anatomical and physiological parameters. Both of them give rise to parameters in the, say, drug biology interaction space. So things like fraction unbound, partition coefficients, permeability. Those are parameters where you that can be estimated both from the physicochemical properties of the drug and from the physiological parameters. So they're kind of mixed parameters. And then finally, there are also information about the study protocol and the formulation that was administered that you need to feed into a PBPK model. Now, once a PBPK model can capture the pharmacokinetics in a reference population, so in this case, in non-pregnant adults adequately, you can translate it to your special population of interest, in this case, the postpartum population. So in doing so, the drug properties obviously remain the same, but the organism properties, I mean, they substantially change. So anatomy and physiology, they are different in the postpartum period compared versus non-pregnant or pre-pregnant adults. And this then also, of course, gives rise to changes in the drug biology interaction. And in some cases, you also may have adjusted administration protocols, so different dosing regimens, and different special events such as food intake or enterohepatic circulation. Although this is something that we did not consider in the amoxicillin PBPK model that I'll present. So looking then at the drug, at amoxicillin itself, I mean, I guess most of you are clinicians, so you all know that better than me. It's a penicillin antibiotic. Has a molecular weight of 360, so not small, but I mean neither not very large. The lipophilicity is around 0, so that means basically that you have almost equal distribution between a water phase and the lipid phase, the octanol phase. It has a relatively high fraction unbound, 0.85 in pre-pregnant adults, and using the method from McMurray and Alcon that I've presented a few slides earlier, you can then calculate a fraction unbound of 90% in postpartum individuals. Amoxicillin is predominantly eliminated as unchanged drug via the kidneys. So 60 to 80% of the dose are excreted via the kidneys, both via glomerular filtration and via tubular secretion. There's also then a minor elimination pathway. So the remainder, 20 to 40%, are metabolized to penicilloid acid via an enzyme that has not yet been identified. Luckily, there were quite a couple of clinical data available that we could use to evaluate our model. Well, first of all, to train the model for a non-pregnant or pre-pregnant individuals, and then to evaluate it in pregnancy and in the postpartum phase. In all cases, amoxicillin was administered intravenously, either as infusion or as bolus. From doses ranging from 250 to 1000 milligram in our reference subjects, so normal adults. During pregnancy, then, we found clinical data in the literature that reported pharmacokinetics after IV administration of 2000 milligram, and in the postpartum period, we found clinical data in the literature that reported the pharmacokinetics after administration of 1000 milligram. Okay, so the first step, as I said before, was then to develop a PBPK model for the reference population, so non-pregnant adults. On this slide here, you can see then the model performance for each of the 6 different studies that we collected from the literature. The circles indicate the observed data. In all cases except for panel E, I think the observed data were expressed as arithmetic means. I think in E it was a geometric means, if I'm not wrong. And the solid line is then the simulated arithmetic mean or geometric mean concentration in case of panel E. And the shaded area is the simulated 5th to 95th percentile range. Now, all of these models are freely available on OSP GitHub. The link is given here. Overall, we were quite confident that that our model can capture the pharmacokinetics in non-pregnant adults quite well. So therefore, we translated the model to the postpartum period. So that means we exchanged all system-specific parameters, anatomical and physiological parameters of pre-pregnant adults with the values that we've collected for the postpartum individuals. Now, in this case, we also had pharmacokinetics in pregnancy just before delivery at a mean gestational age of 35 weeks. We also predicted the pharmacokinetics there just to be sure that we capture the pharmacokinetics well along the course of pregnancy and then as we go into the postpartum period. So in the left panel, the circles are again the observed individual data, and the solid line is the predicted median in pregnant subjects. And the dashed blue line is the predicted median in a non-pregnant population that had the same body weight as the pregnant individuals here. So I mean, of course, during pregnancy, I mean, pregnant women gain weight, and if you correct for that weight gain, then you would come up with the dashed blue line here. Overall, the pregnancy PBPK model described the data quite well. So then we went a step further and predicted pharmacokinetics in the postpartum period. And there we had data that were obtained very shortly after delivery. I think it was 2.4 hours on average after delivery. This is shown on the right panel here. Overall, the model captures the data adequately, although I mean, the model seems to like overestimate concentrations in the terminal phase here. So maybe clearance was not adequately captured. Maybe clearance in our model was too low. The dashed blue line shows the predicted median in a pre-pregnant body weight matched subjects. And what is quite interesting here is that we see that the difference between the dashed blue line and the solid orange line is quite small. So meaning that once you correct already the subject for the, say, pre-pregnant subjects for a different body weight that women have 2 hours after delivery, you can already obtain PK predictions that are, say, in quite good agreement with the observed data. Now, of course, if you integrate then all these physiological changes in the postpartum period, you can still improve the model predictions a bit, as the orange line is still in slightly better agreement with the observed data. But as I said before, the clearance might have been somewhat underestimated by the model. Now that's a very interesting point because I mean, the study where these observed data were measured was conducted in the Netherlands, and unfortunately, the study only reported the body weight, but not the body height of the postpartum individuals. Body weight was above the average what we would have expected for 2 hours after delivery. But because the body height was not reported, we didn't know whether the subjects included in this study are they taller, or are they just say a bit fattier? Did they just have more fat mass resulting in a higher weight, or was the higher weight also correlated with a higher body height, which would then translate also in larger organ volumes, larger kidney volume, which then eventually would also result in a higher clearance. Unfortunately, we could not answer this question because this information was not given. But I mean, it stresses the importance of really having all or having many covariates, and especially body height and body weight, or alternatively the BMI, reported in clinical studies. Now, to summary, to summarize what I've talked about so far, for many physiological model parameters, data on the changes in the postpartum period are scarce, lacking, or even conflicting. For example, renal plasma flow or glomerular filtration rate. There were clearly some, say, gaps in the data that we had, and it's not clear yet whether the trends that were described by the functions that we fitted to the data are really correct. So definitely more data would help here to better inform the functions. And as a consequence of this, say, uncertainty in the observed physiological data, we also have some uncertainty in the parameterization of the postpartum PBPK model. As I said before, additional uncertainty, specifically for the PBPK model for amoxicillin, stems from the fact that covariate information was missing. Specifically, the body height was unfortunately not reported. Further clinical data and then also modeling studies are clearly needed to evaluate the parameterization of the postpartum PBPK model. So, I mean, here we just looked at amoxicillin at one particular point in time after delivery, but that's clearly not enough. So you definitely need more models for different types of drugs and different stages after delivery to gain further confidence in the postpartum PBPK model parameterization. Also for, I mean, amoxicillin is predominantly eliminated via the kidneys. We didn't look at potential changes in the activity of drug metabolizing enzymes and drug transporters in the postpartum period. So that's also a knowledge gap, and that's quite relevant for many drugs. So more research is also needed to fill this knowledge gap. And finally, various extensions of the postpartum PBPK model would be desirable. For example, for oral administration. So the example I've shown was only for intravenous administration. And finally, also for breastfeeding populations. And that's then also a very short outlook I want to give. So the application of the postpartum PBPK model to breastfeeding women. This was done very recently by Kate Job and colleagues. So they included a breast milk compartment in the postpartum PBPK model structure, and predicted ondansetron pharmacokinetics in plasma and in breast milk following IV administration of 4 milligram every 8 hours to women who were in the first week postpartum. I think on average it was 2 days postpartum. The model structure is shown in the middle panel, and on the right panel here you can see then the predicted concentrations in the plasma in red and in the milk in blue. And the pharmacokinetic predictions were evaluated with data coming from the CUDDLE study. And well, the model was then eventually used to estimate the daily infant dose, which is given in the table below, as well as the estimated relative infant dose compared to the standard maternal dose and compared to the standard infant dose. And I mean, here as well, all model files are freely available on OSP GitHub. The link is given again here. So concluding this talk, where to find further information, I've presented say study results from two different studies. The first one, the major part, was from the amoxicillin study, which is shown here. And then in the Outlook, I looked at the say the extension of the postpartum PBPK model to the lactation period, or to lactation in itself, which is described in detail in this study. And finally, I want to acknowledge all colleagues who have been involved in the studies that I've presented here, especially the colleagues above here. They were involved in the amoxicillin PBPK model development, and especially Thomas Eising, Anneke Himstedt, and Georg Kempel did a very good job here. They really helped at many ends. And then also I want to thank, of course, the colleagues shown here below who were involved in the development of the lactation PBPK model, especially Kate Job and Kevin Watt from University of Utah. With that, I'm happy to take any questions.
Great. Thank you, Dr. Dallmann. With that, we'll take any questions that anyone may have. Feel free to raise your hand or type the questions in the chat. So while we're waiting, I will ask one question. I know there's a relative limited amount of data on the changes postpartum, but were you able to look at any covariates such as the method of delivery or whether the woman was breastfeeding or not breastfeeding in your studies?
I mean, that's an extremely relevant question. And I fully agree. I mean, the type of delivery, whether it's C-section or natural delivery, I mean, the amount of blood lost is, for example, different, and therefore you have, or it's plausible that you have different plasma volumes in the end. Also, breastfeeding is an important covariate. Unfortunately, I mean, the data were so limited that we could not look into that. We tried to look for some parameters. We tried to look into that, but then again, the variability itself was so large. Even if you would say split groups according to the different covariates, that the effect was just not significant in the end. But I mean, it's definitely an important point that should be looked at in further well-designed studies.
Great. Looks like we have one question in the chat. Why did you compare the pregnant PBPK with that immediately after delivery for amoxicillin?
Well, that was just because the postpartum PBPK model was just, I think, 2 hours after delivery, so very close to, say, many parameters were very close to the end of pregnancy, except for a few ones like plasma volume, because you have blood loss and so on. But many other parameters, such as renal plasma flow, glomerular filtration rate, were very close to the, say, to the value that you observe at the end of pregnancy. And therefore, we wanted to know if we can also describe the pharmacokinetics at the very end of pregnancy, so just before delivery, because that gave us some information. For example, we've seen that the clearance in the postpartum PBPK model is slightly too low, maybe. But in the pregnancy PBPK model, we haven't seen that. So that, I mean, that gave us some like indication that it's really an issue of, say, the parameterization of the postpartum model, but not itself of, say, how we have integrated the renal clearance in the model itself.
All right. Great. There's another question in the chat from Alamika. The data presented for amoxicillin was immediately postpartum. How far out do you think modeling can predict the postpartum PK? So up to 1, 2, 3 weeks. And are there types of drugs where we have more confidence than others?
Well, I think probably the more you wait, the more the pharmacokinetics will resemble the pharmacokinetics just in pre-pregnant individuals. And I mean, we've seen that many parameters, physiological parameters, return to their pre-pregnant baseline value by 2 to 3 weeks. I think by 6 weeks after delivery, almost all have returned to their pre-pregnant level. So I would say 6 weeks after delivery, I wouldn't expect great differences in the pharmacokinetics between, say, postpartum individuals and just normal women that are not in the postpartum phase anymore. Except if you look obviously on breast milk concentrations, but I mean that this compartment is so small in size, so I don't expect that this has a large influence on overall pharmacokinetics.
I think you just answered the last question, and actually a question I had is what time could you describe as the ideal postpartum time for PK studies? So I think you answered that we typically assume that by 6 weeks physiology has returned to more non-pregnant normalcy. And so at that point, would you suspect that that's the best, after 6 weeks would be a appropriate time?
Yeah, I would say so. I mean, like in view of the data that we collected from the literature, I would definitely say 6 weeks is a reasonable assumption. With the only exception that we didn't look at transporters and enzyme activities. And I mean, during postpartum period, of course, hormone concentrations, hormone levels may still be different compared to the pre-pregnant level, and they may have an impact on, say, the expression of specific enzymes. But that's something where we didn't look into that in detail. So clearly, more studies would be helpful here.
Great. Then a question on the ondansetron breastfeeding model. Did you model the passage of milk by passive or active transport?
Well, that's a good question. I would have to check, but if I'm not wrong, the transfer into the milk was say modeled as say instantaneous via just say a very high influx rate. And then the partitioning between plasma and milk, that was predicted based on physicochemical properties of the drug. Now there are different types of functions out there in the literature that you can use to predict the ratio between milk and plasma concentrations. And essentially we assumed in the ondansetron model that say the rate at which the drug goes into the milk is not a limiting step here, but that it's really say more the ratio that is relevant here. But I to be sure, I would need to check that again. I'm sorry, I can't answer that in full detail.
I don't see any other questions. If you have one, feel free to raise your hand or reach out to Dr. Dallmann after the seminar is completed. I'm sure he'll be happy to answer your questions at that time. So and with that, I will close our seminar today. Thank you very much, Dr. Dallmann, for your presentation.
Thank you for the invitation. Have a nice evening all.
Thank you.